Welcome everybody. Here with okay. Let's show this. All right, cool. Okay, so let's get started. We have a bit to go through. So yeah, welcome to the lecture 6. So finally, we're gonna use some of the modern tools. So we did a lot of preparatory work, and now we're gonna tie all of these things together and learn some of the tricks that kind of made deep learning work in the last couple of years. Okay, so recap from last week. So last week we mostly talked about automatic differentiation. It's basically the approach of having programming languages in which you can automatically get gradients. So you not only do you have like input and output for a program, as in C++ and so on, but you get input, output, and the gradients with respect to the input, so which is very powerful because all of kind of deep learning is basically trying to optimize highly parameterized computer programs using gradient descent. So having efficient and consistent way to calculate gradients is very important. And so we went through it kind of in a fairly mathematical way, but then in the exercise you've seen that all of this is kind of nicely wrapped together in machine learning frameworks. And so just kind of what I said last week is that at the core, most of the major machine learning frameworks are really kind of thought of as differentiable programming languages. So they're programming languages in which you can just write a computer program as you would normally do, right? And then this computer program we discussed could be described as a graph. So here we have 3 inputs, and then there's an intermediate value called B1, which is kind of dependent on A1 and A2, and then those things then go through like a more complicated function that depends on B1 and A3, and then we return our output. So we can always, so any type of computer program, at least, I mean, okay, so let's ignore loops and so on for now. You can, any type of kind of simple computer program, you can always describe as a computational graph, right? And then this was the hook for us to get into automatic differentiation. But when we described automatic differentiation, we were really talking a lot about like matrices and matrix multiplication and, only like simple composition. And so we needed to do a little bit of work on, so we started on the matrix side and then we ended on the graph side. And so now we'll go back for a second. And so basically the way to normalize this again into kind of like the standard kind of matrix vector product type picture is that you can always think of, okay, here, there's one edge that is jumping the layer, right? So it's going from the first to the third directly as this edge, but you can kind of imagine in your head that actually what is happening is that you kind of have like a dummy variable that is like at the same level. And now you don't have these jumping edges, and then they go from each layer to each layer. And so the edges only kind of bridge one type of layer. And so once we have this, basically, okay, what do we notice here? So this almost looked like what we had for the matrix multiplication, but we don't have all the edges, right? So for example, A3 doesn't really influence B1, right? And so we discussed that these types of lacking edges, this is more or less what makes matrix vector products efficient, that you can kind of, instead of storing all of the zeros and so on in the Jacobian, for example, you can just implement the program as matrix vector products, and these types of missing edges and sparsities in the connections is going to be reflected in that program. And so, but we can kind of, if you really want to kind of go back to this matrix picture, you can kind of imagine that there are like these missing edges and they have weight 0, right? And so then we have like a fully connected picture. And this brings us completely back to this matrix vector product picture, which we started in the last lecture. And so we have like our computational graph, and then we have 6 edges in between. So we have 3 inputs and 2 outputs. So 3 times 2 edges, so 6 edges, and they correspond basically to in the normal program to dependencies, and in the gradient program they basically correspond to entries in the Jacobian matrix. And then for the first layer we have 6 edges, and then in the second layer we have 2 inputs and 1 output, so we have a Jacobian matrix that kind of looks like this. And so the matrices are basically the collection of edges, so on. And then basically what we had is, okay, what we want to find is our overall Jacobian or overall gradients. We want to know, okay, what is the derivative of C with respect to A, right? So that's kind of generally what we want to figure out. And so then we had like these tricks last week on how to do this. Basically, we could either kind of slap vectors from the right, or we can slap vectors from the left. And then we can just repeatedly do matrix vector product or vector matrix product as we go along. And so the main thing that we discussed is important for machine learning is backpropagation. So backpropagation is going from the output to the input. And essentially what is going on is that you start with a 1, right? And then you have our vector Jacobian product rule. And so then we can kind of go from the left, and we can multiply. And then in the next step, we get 2 values out once we do this vector matrix product from the left. And then we get our 2 values, which are kind of our intermediate gradients. And then we can go on and do another round of vector matrix products. And then we have our 3 values at the top. And as you can see, we're basically filling kind of like a shadow graph by doing backpropagation, by going basically from the bottom to the top. And then in the end, so what you get through this vector matrix product is 3 values at the very top, and these 3 values identically correspond to this Jacobian, which is the gradients that we actually want to get. And so this is kind of the core of backpropagation. And so it's for us kind of like an efficient way to compute the derivative of this program with respect to the inputs, right? And so that's just a short recap of what we had last week. And so then, okay, we discussed JAX a bit in the exercise, and so you use JAX. So why did we use JAX in the exercise? Because in JAX, this connection, JAX is really trying to be very, very precise in the way how like automatic differentiation is implemented, and you can look under the hood and reason about Jacobian vector products and vector Jacobian products and so on. TensorFlow and PyTorch, they hide this stuff a little bit more, and because differentiable programming as a notion wasn't, only kind of arrived really in the consciousness in the last couple of years. And so, a lot of times it was more, okay, we want to get only backpropagation. And so it seemed to be like a implementation detail. But basically, the way that you can think of kind of how these gradients computations are, or these differentiable programming languages are designed, they're basically NumPy with gradients. So if you can write your program in NumPy using array programming, using things like like the trigonometric functions in NumPy, exponentials, tangent hyperbolicals, whatever, arrays, and like column stack, and all these types of different things. Basically, all of these functions, they usually exist also on the kind of machine learning framework side as a differentiable programming language. What's a little bit annoying is that sometimes the function names are slightly different. And so this is also one of the nice things with JAX, is JAX tries to be kind of like a drop-in replacement for NumPy, whereas in Torch, sometimes instead of concatenate, it's called cat and so on. It's like, so sometimes you need to take a little bit of care, but generally you can think, okay, if you can do like an array level program in NumPy, you can probably write it in something like PyTorch or JAX or TensorFlow. Okay, so then what does this look like? So we did it or went through the exercise how to get gradients in JAX. So in JAX, you had this very nice JAX.grad or JAX.value and grad. And so how does this look like in PyTorch? In PyTorch, it's a little bit weirder in the sense that it's more kind of stateful. And so you're seeing more exactly where kind of you're starting to do backpropagation. And so we have our theories on the left-hand side, where this is the program that we want to do. And then here we have, we write our program in Torch. And then torch basically looks exactly the same thing. So multiplication and addition, and so all of this is overloaded. And so if you want to do like a sign, okay, we do like torch.sign, okay, fine. So it's a very kind of straightforward translation. And so how do we get gradients in PyTorch? So one of the things that we need to kind of say first is, so torch makes the difference between vectors that you want to track gradients for and vectors or tensors that you don't want to track gradients for. So if you want to run our program and get the gradients with respect to our parameters, we need to say, so we are creating our array the same way you would create with NumPy array, but then we need to pass in an additional argument that we say, okay, for this, we want to eventually get gradients of whatever we're computing with respect to this these parameters. And okay, so then we have our parameters, and now we run our program. So we have value equals a program of the parameters, and then we can just print the value. And what happens if we print the gradient? So okay, they're empty, right? So right now nothing happened. We only ran the program and nothing really happened, and there are no gradient stuff. And so what a little bit peculiar in PyTorch is you need to manually trigger now, okay, kind of in a stateful way on the output that you get from your program. You say, okay, dot backward, and this is going to trigger backpropagation. It will exactly basically start now with, slapping this one at the end. It will start at the bottom of this computational graph, and then it will go to the top. What you didn't know is that while you were running this program, it was basically creating or tracking all of these edges and dependencies and so on, so that it knows how to go backwards kind of in this type of fashion. And so this is now what's going on. And so once we have, we triggered dot backward on our output value, we get now our gradients. And so these gradients are the gradients of, the derivative of value with respect to parameters, right? And so this is how you get do backpropagation in PyTorch. What's interesting, or one of the remnants that PyTorch is more like a machine learning framework, not a differentiable programming language, is backpropagation, and PyTorch is much, much easier than forward mode automatic differentiation, which we also discussed, which is matrix vector products. Okay, but so that seems easy enough to do. Okay, you just need to somehow at some point call dot backward, and then everything happens, and then you get your gradients. Okay, so now you might ask, okay, great, so we talked about automatic differentiation. So in principle, now we have all we need. This is our famous learning diagram. So we have our data, we have our kind of loss function, our objective, which variation, amortized variation inference, yada yada. And then our hypothesis set is basically now our space of programs that is highly parameterized, and our learning algorithm is going to be gradient descent, so that we created like specifically a programming language to help us with this, that is in order to make it easy to compute gradients. And somehow we're done, right? Okay, now we can do deep learning, we can go home. And so, but if you remember one of the exercises, we had this exercise early on when we trained our kind of mini multi-layer perceptron with just 2 internal nodes. And so basically it's exactly the same hypothesis space, and it's exactly the same learning algorithm. It's the same number of steps. And so the only thing that is different is the initialization of the network. And so then we can see kind of what happens. And so you see it's basically also the same initialization. There's like a slight difference on the left and on the right. And so let's see how this goes. And so if you start training on the left, it starts training, and then very quickly it finds like a nice decision boundary, right? So excellent. That basically tries to separate the yellow from the blue. Okay, and it's succeeding. And so now if we have kind of our very slightly different initialization on the right, what does learning look like? Basically, it looks like this, right? And so like we did all this fancy stuff like automatic differentiation, gradient descent, and so on, but it's not really learning anything. So it's trying hard, but it's just not happening. And so that tells us, or is a hint that automatic differentiation alone or just gradients alone is not enough to have like an efficient training system. So this is like the world's easiest learning problem that you could have, and so it's already failing, right? Okay. So basically, so what is happening here? So basically, one has a good initialization and the other one has a bad initialization. So what is bad about this initialization? There's a certain kind of symmetry in the data, and the initialization kind of is such that it's aligned with the symmetry and it's not breaking the symmetry. It doesn't know kind of in which way to break this line. Should it break up top or should it break downwards, right? And so having a very highly symmetric initialization, for example, is not a good idea. And this is why this on the left is better and on the right is crap. Okay, so then if you have a bad initialization, if you don't know where to go, maybe not necessarily because you're like in a minimum, but maybe you're also in a maximum, but it's going down the same rate in all directions. You don't know which way to go, right? And so having zero gradients is not great. And so then the left-hand side had our good initialization, which was kind of hand-tuned. And I mean, I gave you this initialization because we didn't talk about initialization. I wanted you to succeed in training your multi-layer perceptron. But clearly, this is not going to scale. Like as we discussed, realistic neural networks have billions of parameters. We're not going to kind of fine-tune how we initialize them kind of one by one. But of course, we're going to fine-tune how to initialize them kind of conceptually. Okay. So so what happens once you initialize this? Basically, okay, this is not going anywhere, and this is going nicely, and it's just like where you started. And so what's kind of interesting in convex optimization, this doesn't happen. So if it's a kind of convex problem, it doesn't really matter where you're initializing, you will always kind of roll downhill and it's a nice convex shape. If you have a non-convex optimization problem like machine learning, it's a bigger problem. Okay, you could also think, okay, maybe, I want to initialize where I want, right? So just get me to the right place. And so maybe like we're also a bit too naive in the way that we run our optimizer. Our optimizers, I mean, it's like nice conceptually, we're going downhill, but it's also kind of dumb, right? We're only going downhill. We're not really looking around us. And so, it's easy to just get stuck and you're just going downhill, and then you're not kind of thinking about what to go. Like if you had a little bit of perspective of what's going on in the landscape, you would maybe see, okay, just like go above this hill and then you'll nicely find a good or better minimum. And so there's also some discussion to be had of should we have a better optimizer, right? And so we're going to discuss this. There's also some things, okay, why is this loss landscape so shitty to begin with? Maybe there are also ways to get a better loss landscape. And so this is more or less what we're going to discuss also about like architecture and so on in the future lectures. So we'll not touch on this this week. Okay, so basically, back propagation multi-layer perceptron have been known for a long time, but I mean there are lots of things where training became difficult, and so for a long time just it didn't work. And so one of the things is basically controlling the initialization of weights, controlling the behavior of gradients, and then controlling kind of the details of the optimizer. And so a lot of the progress in deep learning, even though somehow it seems like there's like a phase transition where we had like a lot of GPUs and we had a lot of data and things started working. At the same time, like an undercurrent was also there are decades of machine learning research that kind of added step-by-step little improvements along the way, and just like at some point there were enough improvement that things just started happening and started to work. Okay, so then basically I somehow oversimplified what machine learning frameworks are in order to make the point that automatic differentiation, differentiable programming is an important point. And so on top of differentiable programming, these machine learning frameworks really kind of give you a lot of the nice tools that were developed over the last couple of years in order to make training basically a one-liner or few-liner, right? So we start with basic hardware support. So can we write programs using multi-dimensional arrays and have them kind of be computed fast? So basically all of deep learning is matrix multiplication. GPUs are great at matrix multiplication, and so just running programs on GPUs is kind of the core thing that machine learning frameworks need to provide. Then we had our automatic differentiation, which is kind of like the foundational layer for you to specify your hypothesis set. And then we have like lots of nice little tools, optimizers, standard architectures, and so on. Again, optimizers. And then we have a lot of like helper APIs in order to build up your training loop and so on, and define your loss function and so on. And so if you wanted to rank the machine learning frameworks, basically JAX's philosophy is basically to only do hardware support and automatic differentiation, and then it's up to, so it's just a programming language, and then it's up to people that write libraries on top of the programming language to have like a nice way to build up neural networks. PyTorch is a little bit more involved, but it's still kind of research heavy. So like if you want to have like a non-standard architecture, it's the best way. Nice way is to do it in PyTorch, which we'll discuss. And then TensorFlow is really kind of the super streamlined, user-facing APIs. If you just want to do like a standard architecture that has been around for a long time, and you just want to be efficient, using Keras and TensorFlow is very good because they're really, really careful about having a nice user interface. And so in this lecture, we're going to use PyTorch for as a middle ground, but it's good to kind of have this rough hierarchy between what the audience is for these frameworks. And then, as we discussed, TensorFlow and JAX are Google, and then PyTorch is backed by Facebook or Meta. Okay, so let's talk a little bit about initialization. It's really one of the key aspects in making deep learning work. And so this is basically what we discussed. Okay, for convex optimization, it doesn't really matter where you're initializing. You'll just roll downhill. Maybe it takes a little bit longer. Maybe you're faster, whatever. You might be lucky. But I mean, you're not going to do anything wrong. For non-convex optimization, it's a problem. And the thing is that deep learning is primarily non-convex, right? So it's not clear that you're like in a nice bowl and you're just rolling downhill. Specifically, for example, double descent that we discussed is an entire like a landscape of equivalent solutions. So there are a lot of flat directions in the loss landscape. And so you want to kind of be able to efficiently explore these flat directions as well. And so somehow like the non-convexity of deep learning is not only like a annoying thing, but it's also kind of part of the power of deep learning. Right. And so, but if we are in this non-convex regime, we need to be a little bit more careful with how we initialize our networks. Okay, so the problem is that deep networks, as we had them, so multi-layer perceptrons where we're stacking. I mean, so so it's nice that we are able to do a lot of composition. So we're stacking a lot of layers, right? Because we want the deep network to basically prepare the data in a way so that the final layer has a nice little easy decision problem, right? But it also means that this deep stacking makes networks extremely sensitive to the initialization of the parameters of the network. And so there you might think, okay, what are possible choices? You might initialize to some constant value for the weights. You might initialize to some standard normal random initialization. So that might be, so this was one of the tricks in the exercise to just randomly initialize, and so you'll not be in the supersymmetric configuration, and it will like just learn, right? And so most of the things that we have done is, okay, we just kind of have standard normal, and so we'll see now kind of why this is bad, or I mean it's already better than like constant value, but it's not perfect yet. And so this is actually still a very, very active area of research on how to initialize these parameters of neural networks. It's not a done deal, but I mean, we already found some good basic ways to do it. Okay, so in order to do this discussion, we can basically think of a neural network. We'll just think about like a multi-layer perceptron. We'll ignore the weights and we'll ignore the nonlinearities. It's a bit weird because we, basically argue that nonlinearities are the main thing that really drive or, incorporate the power of deep neural networks. But I mean, for this discussion, we'll basically just use no nonlinearities and no weights. And so in the end, basically it's just going to be like a bunch of matrices that you're multiplying together, which was kind of the reason why we said, okay, just not having nonlinearities doesn't make any sense, because you can just multiply all these matrices. It's going to be one big matrix and it's just linear. And so, but okay, for this discussion, we'll kind of take this view. And so now we can think about, okay, so let's say our input is distributed kind of like a nice clean way. So it's centered at 0, and it has some kind of variance. So the input values are maybe +1, -1, and so on. And so it's a natural question to ask, to kind of see, okay, what is the sensitivity? So you want to somehow learn the relationship between the output and the input. And so now the question is, okay, what are the gradients? Are the gradients large? Are the gradients small? What is the relationship between output and input? And so a natural question to ask, okay, if we have like a standard unit variance for the input, x, once we pass it through many kind of matrix multiplications, what's going to be the variance of the output, right? Okay, so bad news. So let's say we have our kind of like a nicely centered variable. Basically, we can use some of the basic properties of kind of probability densities. So if you have centered variables and independent variables, you can basically say the product of two numbers, the variance of the product of two numbers is the product of the variances of the two numbers. And then you can also say, if you're adding two numbers, basically the variances add, right? So if you add two random numbers, the variances add, and this is more or less the way that we also do error propagation. Is like it's just the Pythagorean theorem for errors, right? And so when we use these types of kind of building blocks, we can very easily figure out what the variance is once we go through one single matrix multiplication, right? So matrix multiplication is only summing and multiplying. And so because it's summing, we can basically pull the variance into the sum, and then we have the variance of a product, and this we can also split into a product of variances. And so then we can basically see the variance of the output in one matrix multiplication is proportional to the variance of the input times the variances of the matrix elements times the number of kind of vectors. So because in every kind of for every element in the matrix multiplication, you do like a vector product, right, with n entries, and so you're adding n numbers, and so it's basically you're adding random numbers, so you're scaling them, and so we'll basically the variance will be scaled by the number of entries, or like the one of the dimensions of the matrices, right? So if you have our matrix multiplication, we have two dimensions, like the number of input channels and the number of output channels, and the variance of the output is going to scale with the number of input channels. Okay, so this is a single matrix multiply. So let's say we have two matrix multiply. It's going to multiply again. Then we have three matrix multiply. It's going to multiply again. And so we have repeated multiplication, which is nothing else than exponentiation, right? And so that means that, okay, you can get very easily, if you're not super careful, it's very, very easy to get exponential behavior in a deep stack of matrix multiplications, or basically in a deep neural network. And so what kind of exponential behavior can we get? So, okay, if we have like a n times the variance of the weights is greater than 1, basically what we have is exploding outputs, right? So you will have like a, maybe a fairly large variance to begin with, and then, if the variance of the weights is large compared to the number of input channels, then like your outputs just start to explode, right? And so just like a slight change in the input, produces a huge change in the output. And so that's not great, because you completely lose control of what's going on in your neural network. Okay, so then you can say, okay, let's just reduce the variance of the weights, right? I mean, if, for example, if the variance of the weights were 0, then it's 0, okay. But okay, let's say we have a very tiny rate, then you can have the opposite problem. So, I mean, exponentials work both ways, right? So you can either kind of exponentiate a number greater than 1, or you can exponentiate a number smaller than 1, and then if it's smaller than 1, it will just get smaller, and then you have what's called vanishing outputs, right? And so it's also not great, because then basically there's, no matter what the input is, the output is always going to be 0. Okay, that's not a good machine learning system. And so you need to be really, really careful in what you're doing, because you have basically from these repeated matrix multiplication, you have like an expression like this, the number of input channels, for each of these matrices, and then this is basically, like an exponential behavior. Okay, so what is the solution? You can be a little bit careful in the way you initialize these matrices, where you can basically try to make this n times the variance. So this thing, if this is 1, like you don't care, right? So you can stack as many layers as you want, and then it's gonna be like the input variance and the output variance is gonna be the same. And so we can try to do this, but so now realize what's happening. Now for every matrix, the initialization of the weights is different, right? And so originally we said, okay, let's just initialize all of them with the same variance. But now basically we will always look at the scale of the number of input channels, and then according to the scale of the number of input channels, we're going to initialize the weights at the correct scale. And this is specifically designed in order to control the variance of the output of the neural network. Okay. So then the question, okay, now we know, okay, what is the, the forward path. So we know this is the way when we're going, from left to right, from right to left. But of course, like one of the key things in deep learning is backpropagation. And so now the question is, okay, how do we do backpropagation? What is the relationship between the input and the output? So the input, as you might remember, is 1, right? So this is the start of our kind of backpropagation. We start with 1, and then the question, we will backpropagate to get our gradients, right? And so the question is, if we have like a certain scale for the size of the gradient at the output, what is going to be the size of the gradients at the input? And basically here we know, okay, it's going to be only vector Jacobian products, right? So it's exactly kind of the opposite way. And so, but it's still the same type of idea. It's still matrix multiplication. It's just slightly different in the sense that, I mean, it still scales, but now it scales with a different dimension. Because so what are you summing over in this matrix multiplication? You're summing over the number of rows instead of the number of columns, right? And so the thing that is kind of controlling the variance in the vector Jacobian product is the output dimension of the weight matrix. So the same matrix, if, whether or not you want to control the variance in the forward pass or in the backward pass, it will kind of induce a different type of initialization, which is unfortunate because of course you only have one way to initialize it. So, you need to choose one, but you have like diverging goals on how to initialize. But I mean, generally, kind of it's exactly the same type of problem. We can get vanishing gradients, which was a problem a very long time in deep learning. And then you can also, and so what do you have with vanishing gradients? Okay, if your gradients are 0 and you do gradient descent, then you're not going anywhere, right? And so learning will basically just kind of stop. And then you might also have exploding gradients. And then learning is completely, I mean, you're completely disconnected from any type of local true behavior. You're just kind of randomly jumping around your loss landscape. And so vanishing gradients and exploding gradients are not great. And a lot of deep learning is basically about, okay, make all of these gradients well behaved and nice and smooth, and so that your learning can continue kind of in an efficient way. All right, so, but okay, we already know how to solve this. Basically, in order to control the scale of the gradients, we want to basically require that the scale of the Jacobian matrix elements is going to be at the scale of 1 over square root n out, right? And so why is it the Jacobian element? So what are whose variance do you want to control? So in this variance, we want to control the variance of the weight, right? So because it's the weight matrix, And then, so in the backward pass, the matrix multiplies that we do is the Jacobian matrices. And so then, so we want to somehow control the entries of these Jacobian matrices. It's a more indirect way to do it. So we're not talking about the weights yet. There's a nice argument that I'll not go into, that basically this also implies that you need to initialize the weights to the square root of the number of output channels. And so I'm linking a very nice slide by François Fleuret, who generally has a very nice machine learning lecture. So if you want to have like a little bit more mathematical in detail lecture on deep learning, I absolutely recommend this set of slides. And so basically, okay, we're initializing the weights kind of the same way as in the forward pass, but just by looking at the output dimension of the weight matrix instead of the input dimension. Okay, so now we have our two requirements. In order to control our forward, we want to initialize with the number of input dimensions. In order to control our backwards, kind of our gradients, we want to initialize with our number of output dimensions. And so then we need to somehow solve this. And so being democratic as we are, basically, one of the nice approaches here is to just take the average, right? And then you're saying, okay, the variance needs to be the inverse of the average of the input dimension and the output dimensions. For example, if you have a square matrix, it's going to be the same thing. If you have like a hidden like a layer that goes from 1,000 inputs to 100 outputs, then it's quite a bit different. But you can, so it's kind of intuitive to say, okay, we'll just take the average for the variance, and then so that means the standard deviation of the weights when we initialize them randomly either needs to be a square root of that, right? And so basically, as you kind of when you want to initialize your network, you go through your network, you look at each of the kind of components of the network, what kind of weight matrix is associated with it, at least for a multi-layer perceptron. If you have a more complicated architecture, so like you're into differentiable programming and so on, it becomes much more difficult to answer this question. So all of this discussion is geared towards multi-layer perceptrons, and so also kind of goes to the fact that just having differentiable programs is not enough. It's there's some things about deep networks is important, and it's not just about the gradients. Okay, so that's initialization. So I should say the name. So this is called Xavier initialization, and it's one of the default ways to initialize neural networks. So basically, we're taking the mean of the input and output channels. Okay, so initialization, in some ways we know how to deal with this. So we now talk about one of the next tricks to have is data normalization. And so we said, okay, one of the things we want to do is somehow control the variance and the nice behavior of these inputs and outputs. And like all of our discussion was somehow, there's a hidden assumption in our discussion that the expectation value is kind of 0. It's nicely centered, so it's the same number of negative inputs and positive inputs. And all of our activation functions kind of depend on it, right? So like a ReLU, I mean, it's like the decision boundary is at 0, right? And so if all of your decisions are at like -100, like the ReLU is always going to be 0, right? And so like somehow for just the network to function, it's important that all the values that these nodes ever see are somewhat like well behaved around 0 and not, with a kind of okayish variance, right? And so the variance kind of we fixed for initialization, right? And now we need to somehow figure out, okay, we need to somehow also fix the normalization of the inputs. And so this is very easy to achieve. It's one of the standard tricks in machine learning. It's always very good. So if you do like computer vision and you have like pixel values, usually they're like 8-bit values or something like this, from 0 to 256, right? 256 is a number that is far beyond 1, right? And so one of the nice tricks in that you should do in machine learning is always to rescale your inputs so that they're unit variance. And so you can basically subtract the expectation value and divide by the variance of your training data. And then this will give you like a distribution of inputs that is basically nicely centered at 0 and it has the right variance. And so this is really doesn't really affect the data distributions itself. It's just like a uniform scaling and the shift. And so this is more or less the same thing as kind of a choice of units. For example, like we're not kind of communicating in Kelvin, right? So I mean, room temperatures, whatever, 290 Kelvin, right? And so it's very far from 0. It's like just annoying kind of scale to reason about. And so what we're doing is, I mean, so we're scaling. Okay, in Kelvin we're not scaling because centigrade and Kelvin is the same, but we're shifting. So we're shifting to 0 so that we can talk about plus 10 centigrade and minus 10 centigrade. If you're like into Fahrenheit, we are also scaling a bit, and you're choosing units in a way that makes it easy to reason about like the thing that you're trying to do. And so basically, it's like all the behavior or the relationship between different data points, you know, how easy the learning problem is, like generally, and how hard it is, like doesn't really change by scaling. You're just making it numerically more stable and nicer for the learning system, right? And so basically, you subtract the expectation value, divide by the variance, and if you're marginalizing over all of these, all the labels and all the data, you'll get like a nice, I mean, you might not get a Gaussian, but at least the variance, I mean, of course, you're not going to get a Gaussian if it's not Gaussian data, but I mean, at least the variance is kind of roughly at the right scale. The variance is defined for any type of data sample. Okay, so then, so that was easy. So that now we have like a more difficult problem to solve. Okay, so we scaled our inputs and we tuned our initialization. So we know we have like a nice input at like expectation value 0 and like a nice variance. We initialize kind of in a smart way our weights, and so we know the output value is going to be also nice and easy, and you know, like expectation value 0, same scale of variance, and so on. But of course, this is only kind of the first thing that we're doing kind of in learning. So we're initializing. And now the question is, okay, what is happening once you start learning? You know, what is kind of going to happen, right? So we know at the initialization, everything is nice. And then once you start training, you don't know really what's going to happen. And so one of the problems here is called covariate shift. Basically, you know, so what is happening in the deep network? So the upper layers are preparing the data for the lower layers. And so you can kind of think, okay, if you forget about the upper layers, the lower layer is just a neural network that is seeing some data and it needs to solve a learning problem, right? Yeah.
Why do we know that the variance is the same?
Well, because we initialize our weights in a nice way with the Xavier initialization so that we control, we don't have exploding outputs or vanishing outputs, right? So that's no, so yeah, so this is a copy paste. Yeah, so we only know this at the initialization. At training, we don't know what's going on exactly. So
also the variance.
Yeah, the variance we don't know exactly. So this is exactly what we're trying to solve. Yeah, so I'm gonna fix that slide. So basically, yeah, so you have, let's say you have like an upstream network and a downstream network. The role of the upstream network is to kind of prepare the data, and the role of the downstream network is to kind of deal with the data and, you know, might make a final decision. And so you can basically just say, okay, the downstream network has like a learning problem, but the learning problem as you're training is changing all the time. Like it's not like some fixed data set, but because we're changing the parameters of the upstream model, somehow the downstream model like always needs to deal with a slightly different learning problem. And so this is called covariate shift. So what is a covariate? A covariate is just a standard name in statistics that if you have two random numbers that are correlated, you know, or like functions of each other and so on, they're called covariates because they kind of vary together. At least to some degree. And so of course the H1 depends on the X and the H2 depends on X and so on. And Y depends on H1. And so all of these things are correlated values. And so what is happening is that some of these covariates, like the internal representations of the data, they, of course, as you're starting to change your parameters, they're starting to shift, right? And so let's say at the beginning, so you know, we scaled our inputs, we did our nice initialization, right? And so we know, okay, it's gonna be fine. and we have our nicely tuned variances, right? And then, so what is happening now that we're changing the parameters, right? So we're somehow doing our gradient descent thing, and we're changing the parameters of the input. And this, of course, starts shifting around the intermediate outputs. And I mean, it's not bad. It's the role of the input network. But at the same time, somehow now, if you kind of ignore the upper layer and you kind of put yourself in the shoes of the lower layer, so somehow, you know, like we said, okay, input normalization is important, and then the lower layers sees like wildly shifting inputs, and so that's not great. And so, for example, one thing that might be happening, so what we discussed is that like the role of the input networks is, for example, we have like a few decision boundaries, and then with the activation, we created like a curve. So it might be that like the direction of the decision boundary is right. So it's like a useful feature to learn to like split the data into that direction. But we also know that, I mean, there's like there's a kind of degeneracy in the weights, right? So if you have like the like weight 1 and 1, it's like a diagonal decision boundary. If you have the weights 100 and 100, it's also a diagonal decision boundary. So the feature is right, but the scale of the feature is kind of just not good for learning. And so somehow you need to fix this in order it's kind of doing the right thing. So the parameter update already did something useful, but at the same time, like inadvertently, it made the learning problem for the downstream thing slightly more difficult. And then basically what the downstream thing needs to learn is to kind of divide by whatever 100 or something like this to kind of rescale it dynamically. And it's just like it needs to react kind of quite a bit. And so basically then, in order to fix this, there's a system called batch normalization. So batch normalization is basically exactly the same idea as we have kind of in the input data normalization. So we just want to scale our inputs to be, you know, unit variance, or at least some have like a nice controllable variance. And it will basically internally shift all of the data to be kind of at nice little values. So what is going to happen? So if you just kind of compute like an intermediate value with your function, it's going to have like some hidden state. And that might be varied widely depending on what the parameters are. And then what batch normalization is, it will remove the expectation of all the input samples that you have. So we'll look at the empirical distribution of these hidden values. You know, they might be kind of composed of like label 1 and label 0, but there's some global like distribution of hidden states. And it will just subtract the mean value of that and then scale it to unit variance. And then, okay, maybe sometimes it's nice to have it at non-centered value, because maybe you want to push it to a certain type of decision, and the decision boundary is that, you know, for example, you want to push it into like the positive edge of the ReLU or the negative edge, because maybe that type of feature tells you whether or not to turn on one of the neurons or not. And so basically, it's not only doing kind of to 0 and 1. So this is kind of like a preparatory step to kind of get control over the hidden state. And then there are learnable parameters, gamma and beta, to kind of see, okay, what is the optimal population level distribution of these hidden states, right? And so batch normalization kind of plays the same role as data normalization, but it happens kind of internally in the network. Okay, so that's so it's kind of like a nice little trick, but it has a very dramatic effect on the effectiveness of learning. As you can say, it's the same type of neural network. So you learn either with batch normalization or without batch normalization. And so on the left-hand side, if you have like a small learning rate, you know, okay, what is the effect of batch normalization? Is you learn much, much quicker, right? Because I mean, you're helping the network kind of control its decision. It doesn't need to spend time to like react, like if something upstream changes. I mean, already found the right feature, but it's like maybe at the wrong scale. Like it needs to kind of adapt and rescale it. And so you're kind of you know, removing that part of variability, and you make training easier. And so that's why you more quickly arrive at a good good solution, right? And so here it's not loss but accuracy. So higher is better, yeah.
What exactly is a batch?
Yeah, so we'll get to, so, but for now you can say, okay, let's say like in our exercises, we always kind of sample like a batch of 200 examples, right? And so this gives you like a set of hidden values that is like a population. And so presumably it's like related to the overall population of training samples. Okay, so then we have our, we just kind of learn quicker. What is nice is if you're stable, yeah.
With this batch normalization, you do this after each layer, or?
Yeah, so you don't have to do so. I mean, even without batch normalization, you're gonna learn, right? And so now you can kind of start adding layers. So sometimes like people, okay, we'll get to this. So you can do it like after, like it's not super important. You can just add like a few. Okay, so then, okay, so you're learning, like for a small learning rate, you're learning faster. But one of the nice things is, okay, if your training is more stable, you can also kind of trust your direction a little bit more, and you can go to higher learning rates. And so this is then, this is the difference between learning working and not working, right? So here, basically learning is just not doing anything because the learning rate is too high, and like it will like crazy, like, swoosh around these internal activations and nothing is going to happen. But if you're kind of doing this normalization, you're kind of regularizing what is happening during the training process. And then you can go to higher learning rates. What happens if you can go to higher learning rates? You can just learn faster and you'll have your nice machine learning system much quicker. So it's really kind of like a big difference. It's one of the kind of main tricks to use. Once you know how to set up a machine learning, like a multi-layer perceptron, you can start adding things like batch normalization. Okay, so one kind of note. So it's kind of like it seems innocent, and like when you explain it, it seems like obvious or so on. What's kind of weird is that so this is quite a big change in how we think about what the computation is doing. So before we had batch normalization, and the neural network output only depended on the parameters and like my input data, like my image of a cat or something, and like gives me a prediction. And now with batch normalization, somehow like all the other images that I'm also trying to predict, they affect like what my prediction for my little images, right? And so somehow you're coupling these things, and you're coupling them not because it's bad. I mean, it's good because you're trying to learn like what is the population level distribution of these things, and you're trying to shift. And so doing something useful, but it's somehow coupling different data instances together, right? And so like in the true, like once you are done training, you want to do a prediction. Of course, let's say I want to predict like 10 different images of animals. Of course, I don't want to, like, my prediction shouldn't depend on the other. I mean, the entire point of statistical learning theory is that they're IID and so on. And so it was really just kind of like a trick in order to control kind of the behavior of the learning process. And so basically, what is happening is, okay, for training, we'll basically use all the different examples that we have, and we'll kind of learn what a good shift and scaling is going to be. And then once we have trained, during the training, we'll basically have accumulated a lot of experience what a good expectation value of these hidden nodes is going to be. So we'll fix this the same way that we fix our training data. And then this is going to be totally fixed at the test time. And so, there's a difference now for, what the output is going to be during training, and then what the output of a neural network is going to be after the training. And so if you're debugging neural networks and you're trying to figure out, okay, why did something happen in a neural network, it's very often the case that you forget to kind of either kind of fix the batch normalization and so on, and then you're kind of figuring out, okay, why is this type of prediction, wiggling around all the time, because it somehow depends on all the other data items that you have. And so this is very good to keep in mind, as you're kind of debugging. Okay, so then there's a lot of discussion. So there's one discussion, how many batch normalization kind of layers should you have? And then there's also, okay, where do you put it? And so you can put it after the linear layer, and then you can put it after the non-linearity, right? And so where should you put it? Okay, so if you're saying, okay, it makes sense to have it after the linear layer, because basically you're saying, okay, I have my input data, and I'm just gonna, before making a decision, so non-linearity, like the sigmoid functions, whether or not you like fire yes or no, right? And so you basically say, okay, before I make this decision, I want to somehow find like a good unit in which to make this decision, right? And so you say, okay, I do it after the linear layer, right? But then you can also say, okay, which thing is going to affect the distribution, or which is the most unpredictable thing that affects the distribution of my kind of intermediate values? It's not going to be the linear thing, it's going to be the non-linearity, right? Because that's becomes more uncontrollable because it's non-linear, right? Okay, with ReLU it's not, but I mean with sigmoid and so on, like it becomes like a very weird shape. And so these are the things that you want to control. And so you can basically argue for both of these things, and like people are kind of arguing back and forth. So if you're like just Googling, okay, where should I put my batch normalization? You have the first thread. So batch normalization before or after ReLU, then okay, where to place batch normalization before or after, blah, blah. And so it's just basically people discuss without end. And the basic fact is, okay, it just doesn't really matter, right? And so it's so Sebastian Raschke is a machine learning professor, and I mean even within experts, like people just okay, whatever. So you can just argue for both things, and there was like a specific choice in the original paper for batch normalization that argued like in a very specific way. But then like some of those people now also switch where they put the batch normalization. So you can just try both things and then just don't think about it. Okay, so then one last thing is that, okay, batch normalization started like an entire trend of adding like these regularizing approaches while you're training. So there's now layer normalization, and then you're basically trying to control the difference between the individual like activations. So as we said, so in the layer, like every kind of node in the layer is like a different feature. So we had like multiple features, right? And then we had our non-linearity to combine them maybe in these things. So it's useful, like if you want to combine them, it's useful to have them all at the same scale. So there's like things like layer normalization, instance normalization if you have like a single pixel, and then you want to of course have like all of the different channels like red, green, and blue, or the kind of the appropriate thing for the hidden layers. You want to have them kind of normalized. There's group normalization and so on. So there's lots of different normalization techniques now. But I mean, batch normalization is kind of one of the first ones, and it's a good default choice to use if you don't have like a specific reason why you want to kind of use a different type of normalization. Okay, so we figured out, okay, we can already improve training a little, or stabilize training by kind of doing a bit more computation. And now we want to talk a little bit about optimization. So we said, okay, initialization is important if you stick with your optimization algorithm, right? Because optimization, like gradient descent is just going to go downward, and so then it like matters where you are. You could also take the different view and say, okay, I want to keep doing gradient descent. I want to keep my neural network and like don't worry about initialization. And maybe instead of worrying about initialization, I want to improve my optimization, right? And so we're going to talk about this flip side. And so far we've been quite naive about optimizing because somehow, we found like a nice way. It's very intuitive and so on, and seemed okay. There's, why should you think about it so on? Okay, you want to minimize something, just go downwards, right? And so that's somehow the beauty of gradient descent. And we spent a lot of work into, computing gradients and so on. And so clearly we don't want to change it a lot, but there's still like some things that we can look at. And specifically, okay, what can we look at? We can look at the gradient and we can look at the learning rate. So there are two things to look at. So we'll look at both of them. Okay, so let's look at the gradient. Okay, so what is the gradient? So basically, when we had all of our like discussion about empirical risk minimization and so on, basically what we want to have is the gradient of the loss function, which is an expectation value over the population of input samples, which we assume to be IID and so on. Then we discuss, okay, we cannot compute the expectation value because it's a likelihood-free problem. We don't know. We only have samples. We don't, we cannot do this integral. And so, but then we said, okay, we can do it like an empirical estimate of this expectation value, which is just the sum of the individual gradients, and then divided by the number of samples that you have, and it's just a standard like Monte Carlo estimate of an expectation value, right? And so why can we move the gradient sign into the expectation? Because that's like a linear operation, and so you can move the gradient through the sum or through the integral under some regularity assumptions. And so basically, like the gradient, the overall gradient of the full data set is going to be like the mean of the gradients of each individual sample, right? And so then, because it's an like an estimate, it's not, we don't know exactly what the gradient is going to be. We know it's going to be a random number because the samples that you estimate the gradient with are going to be random. And so it's a random number. It has some mean value. We know it's an unbiased estimate. So the mean of these estimates, if you try to do this multiple times, you get the right estimate of the right gradient. But there's also some kind of variance kind of associated to it. And so now we can kind of think about this variance a bit. And so the full, like, okay, let's say we have 1,000 input samples. And so we use like our, 1,000 input samples to estimate our gradients, that's great, but it's not the only way we could estimate the gradient. We could also just use like 900, right? It's also a gradient estimate. We can use 500 and so on. And so any subset of the data is also just going to be a very unbiased estimate of the data. If you're not kind of careful in like which samples you use to estimate the gradient, if you're kind of randomly selecting ones, then it's going to be an unbiased estimate, and you can use any one of these things. And so now you start questioning, okay, so what is the effect of using less samples to estimate the gradient? It will basically increase the variance. So with the full data set, you use all the information that you ever had to estimate the gradient. Great, it's going to be a small variance. If you use like half of the data, it's going to be, higher variance. If you use a quarter of the data, it's going to be even higher variance. And so now it's the question, okay, what variance do you need in order to do it? So somehow, even with 20 examples, you already have a gradient estimate, and you could go like gradient descent, right? And so do you actually need like to compute the gradients on all of these examples? So that's the question basically we need to answer. One kind of special case is even like the gradient of a single example is the unbiased estimate of the full gradient of the thing, right? It's a super high variance, but it's unbiased and, already gives you a signal, right? It's just very, very noisy. And so this is basically the step of going to n equals 1, right? And just a super high variance gradient. Okay, so this is sometimes, so all of these things are stochastic gradient estimates, right? And so sometimes when we go to n equals 1, this is specifically, like if you talk about stochastic gradients, sometimes it refers to specifically n equals 1. Okay, so now let's have a discussion. Is it good or bad? So should we have very high variance or very low variance? Naively, you would think, okay, I want to have I want to do my best job at gradient descent as I can. I want to have the best gradient, and so I'll just use all the data that I have, and I'll just go. And so now let's see what is happening. So we start with our initialization. We have our nice kind of little loss landscape, and so doesn't matter. So here the gradient is clearly wrong. So we have our gradient estimate is high variance, and somehow like it's not really pointing in the right direction. On average it will point kind of downwards, but sometimes it will go a little bit higher, a little bit lower. And so, okay, what is happening here? We'll not go anywhere for this step because the gradient is 0. So we're neither going left nor right. So, okay, I clicked, but you see nothing happens because the gradient is 0. But then, so for the next step, okay, now our estimate is, like a little bit too steep. So we're going too far. So now if we do like a gradient descent, we'll go too far than we should have because we kind of estimate our gradient to be super long. There might also be a case where the gradients like switch a sign. If you're like close to like a 0 gradient, like you have finite variance, and sometimes the sign is going to switch, right? And so sometimes you're going like the back, like in a wrong direction, and so on, and then you're go. And so it's kind of like a noisy process, but somehow, because on average these gradients are fine, it's gonna work out, right? And so specifically, if the sign is correct, you're at least going in the right direction, right? And you don't care, okay, maybe the scale is not correct, but you're going in the right direction. And so just to have like an example, so this is like an example from my own research. And so it's basically testing like different types of stochastic gradient computations for like particle physics applications. And so you can see, so the loss landscape, which I kind of computed by hand, kind of in a painstaking way, is the black line. And then the gradient estimate is the yellow line, which is the tangent. And then let's see, on the right-hand side, you see the loss. And let's see how this gradient optimization works. It's a highly noisy gradient. It's not the best gradient in the world. And so you're seeing it's kind of wiggling around a lot, but the optimization still works, right? So on the right-hand side, you're seeing, okay, you're minimizing, but okay, you're not only going downwards because your gradient something also like points in the wrong direction. And so you go upwards sometimes, but okay, it's fine. Like things work out, even with super noisy gradients. If you were asking me, okay, is this a good gradient? I mean, like sometimes it's like a horrible gradient, but somehow the direction is fine, and then it works. Okay, so highly noisy gradients are not bad. At least they're not kind of killing your optimization. And so then what's kind of interesting is gradient optimization, like highly noisy gradients can help you in non-convex optimization settings. So let's say we have our like gradient descent. We're saying, okay, we're going down, and then now like this will tell us to go back to the right. And so let's say this is now wrong gradient, right? Because so it should be 0 because it's kind of close to the local minimum, but it's somehow kind of by chance pointing to right. And then so you jump up through this thing, and then you actually can go down. So highly noisy gradients just help you kind of ignore these like a lot of like local minima and so on. It will like help explore the loss landscape in a stochastic way, and you're not totally bound by gradient descent, right?
And then some temperature to these gradients.
So we're going to talk about that. So that's the next step. So somehow, yeah, so somehow it's defined by the scale. Okay, if you had like only random walk, right? So you could also say we're optimizing our loss and we just ignore gradients. We don't have gradients. We just randomly walk through the loss landscape and then let's see where we end up. So this Brownian motion also works, you know, but so you're basically trading off like some randomness, like random exploration with some targeted direction optimization. And so gradient gives you direction, the noise gives you like exploration, and that helps you kind of defend against, you know, some of the trickiness of gradient optimization. So for non-convex, like, okay, you don't want to do this, but for convex optimization, for non-convex, it's helpful. Okay, great. So it's not a bug, it's actually a feature, helps us jump out of local minimum. Okay, so then we have basically a trade-off to do. So we can do either like single data, like a single instance as our noisiest gradient we could ever have, or we have all the data that we ever have in our training data set, which will give us the best gradient we could have. And so now we are basically trading off. So the single data is cheap to compute per iteration because we're only kind of doing one forward pass. Gives us very less accurate gradient, so we'll likely need more iterations, but we're also faster. We know that the noise can help, so that's great. But then the full data, also sometimes called full batch gradient descent, it's expensive to compute, and often it's impossible to compute. If you have like a terabyte of input data and you're running this through a neural network, like you know, you have like billions of internal activations and so on, like it just doesn't fit into memory. And so to some degree, you can, I mean, it's not necessary and also sometimes not possible to compute the full data batch gradient descent, at least not easily. Then, I mean, we get a more accurate gradient with few iterations. But we also know that taking the gradient literally can hurt exploration. But there's an additional advantage to this. So I talked about GPUs, and GPUs are very good at highly parallel computation. So somehow, going from the left to right is, I mean, it's more computationally expensive, but also not that much, right? And so if you have a highly kind of parallel computation machine, you can actually afford to compute many things at the same time in a fairly fast way. And so it's a trade-off to do. And so basically what happens is like a speed well, it's called mini batch stochastic gradient descent. And it's exactly what we've been doing in all of our exercises. We always sampled like 200 examples, and then we ran our data. And so basically your mini batch, you're trading off, okay, how accurate are your gradients? How much noise do you want to have? And so it kind of partly answers your question. So in some sense, like the size of the mini batch like controls the noise of the gradient.
Both sides get faster, or my gradient probably that's how you able to figure that.
Yeah, exactly. So yeah, people do lots of tricks like this. Okay, so then okay, we need to speed up a bit. So let's we have our momentum. We have the second thing. We said we're going to look at two things. So we have our gradient, and then we have our learning rate. And so let's look at the learning rate, and this is under the headline of momentum. It's also kind of in the direction of your question. Okay, so we had our learning rate, and so the way that we designed our gradient update is like a fixed learning rate for all of our training, right? But our loss landscape has kind of areas where it's easy to learn. It has areas where it's hard to learn or where you need to be more careful. If you have a super smooth loss landscape, you want to go fast. You want to you trust your gradient a lot. Like it will basically, you want to go far into the future and like, okay, go. Once you go into like an area of the loss landscape where there's a lot of kind of internal structure, you want to be careful. I mean, maybe you want to also jump, but I mean, at least you want to know that you're like in an area where there's a lot of structure. If there's no structure, like you just go. And so somehow you want to have like as you're rolling down the hill, you want to basically have like something like a gas pedal to react to what your environment is and kind of adjust your training, right? It's the same thing if you're, running, right? Or like on a Autobahn, you go like 160 because there's nothing changing in your environment. You can go fast. Like if you're like in a city, you'll not go 160 kilometers per hour. I hope not. Okay, so then, okay, so how do we do this? Basically, what we can do is we can kind of tune our update rule and the same type of idea. Okay, let's just trust the gradient less. And so our current update rule, so we have our old parameters minus the new, or like some update, which is lambda times the gradient. And so that was our system, but we could also say, okay, somehow we can have like a mixture between the old gradient, like, what we have been doing, and the new information that we get, which is the local gradient that we get. And it's basically some kind of mixture of information, like, your personal kind of training history and the local environment of what's going on, right? And so this is just another version of, not taking the gradient too seriously and, have some kind of memory or understanding on what your training dynamics are. And so this is called momentum. Why is it called momentum? Because so we can kind of imagine, okay, if we have like gradient zero, we're like in a flat space. Okay, how does our update rule change? Basically, it's going to be just scaling up the gradient, right? And so you're scaling, let's say by 1.2, and then next time you're scaling, by 1.2 squared, and you're accelerating actually. And so that's really nice. You're just, like if nothing is changing, if you get no information from the gradient, you're accelerating your training, and you're apparently in a flat area, and you just want to get through this flat area as fast as possible. Okay, so that's nice. And so, I mean, it's nice in two ways. It just keeps going, like it doesn't stop. Like if you just had gradient zero, like you wouldn't even update the parameters, but it's not only just keeping going, it's even accelerating. Okay, so this is what it looks like. So you have gradient descent in blue and gradient descent with momentum. You see it's a little bit more janky in the sense that it's overshooting, right? But it's faster, right? So even though like it explores kind of crazy regions of the loss landscape, like it gets to the minimum much quicker than just gradient descent, which is very, very slow. And so this is kind of scientific version of this. There's also a non-scientific version of this. All right, so that's stochastic gradient descent with momentum. All right. Okay, so we have one more thing to get through. So deep learning is all about high dimensions. We always had like our little like one-dimensional thing, right? But clearly the structure of the loss landscape, depending on which direction you're looking, is different, right? So like in the Autobahn, if you look straight, nothing is changing. If you go like directly to the right, lots of things are changing, right? And so you want to somehow be aware of which dimension is actually kind of relevant. And so somehow you want to tune your learning rate to the local like space frequency in each coordinate, like independently, right? Instead of just being tied to one global learning rate. And so let's see how this goes. Basically, so this is a system called AdaGrad. It's an adaptive gradient descent, and basically adds a per parameter learning rate. And the per parameter learning rate is like the inverse of the historical gradient information that you get. If you're doing training and you're noticing, okay, the gradient in this direction is always super high, that means there's like a lot of structure, like a lot of change happening. And so here, like I should be a little bit more careful about not taking too big of steps. And then if they're like if you're looking in a different direction, there the gradients are 0, then you can afford a large learning rate, and then you can just go, right? And so you want to kind of scale by the inverse of the size of the gradient. And so the sum is like all the training steps you're accumulating as you're training your like bookkeeping and seeing, okay, which directions in the loss landscape are important and which directions are not important. Okay, so then there are lots of optimizers. So these were only 2. So there's stochastic gradient descent, AdaGrad, there's RMS prob, and so on. I mean, there's like it's an entire research field of optimization, right? So we're not the experts here. So there are lots of optimizers, and so one of the nice things that deep learning gives you is gives you access to all of these optimizers without needing to code these things by hand. So I kind of put you through the pain of writing your gradient descent by hand, mostly because it's good to have it done once, but then you never want to do it again, right? Same with gradients. Okay, so then how do we do this? So one of the default choices in deep learning is Adam. It's basically like a good combination of these 2 things that we discussed, momentum and per parameter scaling based on historical kind of information about the loss landscape. And so the way that we have it in PyTorch, so PyTorch has a very generic optimizer API. And so basically you're saying, okay, I want to run Adam as an optimizer. And then you give it like which parameters are you supposed to be optimizing. And let's say you have some kind of loss function. You do the dot backwards to trigger back propagation. Now you have gradients. And then you say optimize the dot step, and it will adjust. It will take the gradient because it knows where to find them, because it knows about the parameters, and it will like adjust the parameter value. What's a little bit annoying with PyTorch is it will not kind of reset the gradient, right? And so it's important to reset the gradients for the next step, right? Because you don't want to start accumulating gradients all the time. I don't know why they thought it's a good idea, but okay. So it's just a frequent error source of bugs to not reset the gradients in your optimization loop, but it's a very simple API, and you can say, okay, if you want to use like a different optimization algorithm, you just, instead of torch optim Adam, you put in something else, right? And you'll see if you look at the API documentation, there are lots of cases or lots of optimizers to choose from. And it's, even though Adam is one of the default choices, not necessarily the best everywhere. But there are lots of things, and it's useful. I mean, Adam, I would say, it's a good thing to just start with and like see, okay, are things going fine? But then like there are some cases where other optimizers are better, and so you can see here like different types of optimizers. They all kind of get the same. So our sweet little stochastic gradient descent is the slowest. But yeah, they all kind of do the right thing, but they take different paths. And I mean, it depends on the loss landscape and so on, but there's no universally best optimizer. And so it's just start with Adam and then, see where you get. Okay, so then for the last 7 minutes, we're gonna basically put all of these things together and, create our nice machine learning system using all of the nice tools that have been developed over the last couple of years. And okay, so now on top, so we started with just, okay, we solved machine learning by doing differentiable programming. But now we added quite a bit of on top of automatic differentiation. We added optimizers. We added, kind of being thoughtful about normalization, like data normalization, internal covariate normalization, initializations, and so on. And doing all of these things by hand is super annoying. I hope the exercises showed you that. Basically, like there would be no papers in machine learning if you had to do this by hand. And so all the machine learning frameworks are designed to make this as painless as possible. And so the first thing we need to do is, okay, how do we write a parameterized function? And so deep learning is all about having functions that are a function of two things, the data and the parameters, right? But there are like a deep conceptual difference between the data and the parameters, right? For example, the parameters are things you want to optimize, and then the data is just the data that you have. And so basically it's better, like the parameters are better thought to be like a property of the function instead of like an input to the function. I mean, you can think of it either way, but I mean, it's useful sometimes to like just, think of it as a think of the function, which we mathematically often express as just like a subscript. So that's math. How do we do this in code? So there's a function objects. So if you're at like a programming class or have thought about like functors and so on, basically you can have a function like a object, like an object-oriented programming thing, where you overload the call method, like what happens when you do like parentheses open into the whatever. And so it's not a function, but a function object. And so it's basically like a subclass of Torch gives you like a nice subclass called Torch NN module, and will basically allow you to define such a function that has its properties parameters. So you say, okay, you're initializing your function object with some parameters. So the Torch NN parameter, you're initializing the parameters to some values, and then whatever you put in forward will basically be what happens if you call the thing with parentheses, right? And so how do we do this? So we are creating our function thing. We are creating some inputs. We call it as if it was like a standard Python function, but in the kind of background, kind of this forward thing happens. And this actually holds the actual logic of what happens when you execute this function. But, as a user, it just looks like a nice function. It's exactly the way you want it to be. And what's nice is that because it's a function object, so with the normal Python function, the only thing you could ever do is just call the function. With the function object, you can ask the function like different questions about its parameters or about its properties. And so one of the main properties we are interested in is like, what are your parameters? Because this is the thing we want to stick into the optimizer, right? And so here you can basically say func.parameters, and we'll give you like a list of parameters. And what's nice is if you use this torch nn.parameter, I said in the beginning, like Torch has this weird thing that you need to say, okay, these are tensors I want to have like gradients with respect to. And so it's easy to forget. This requires grad equals true. And if you just wrap it and say, okay, this is a parameter, it will automatically configure your parameter tensors to be kind of sensitive to automatic differentiation. Okay, great. So very nice. So then we have our kind of function object, and that defines our hypothesis space in our learning theory setup. And so now we can, write our nice little perceptron that we also had in our exercises in a nice way. We have our weights and we have our biases. We initialize them at some values. And then we do our matrix multiplication. If you don't know about einsum, I highly recommend you to read about it. It's an extremely nice function, which basically eliminates 90% of torch because you can all like express it as einsum. And then so you basically do a matrix multiplication and you add your bias, and then you put it through your sigmoid, and then you're done, right? So this is a perceptron, but now using cutting edge machine learning tools. Okay. Not very impressive, but I mean, you can at least do it. Okay, so then one of the nice things, as I said, okay, once we get access to the parameters, we can just kind of stick it into our optimizer. So great. And so now like the last couple of things. So, it's nice that PyTorch gives you like this entire view of differentiable programming. If you want to do like machine learning research, it's useful because you want to try like different types of architectures and so on. But realistically, there are lots of standard architectures that you want to reuse. And so Also at the same time, we also haven't really included our nice initialization scheme anywhere. So here we're still initializing kind of by hand, right, our parameters. So what is happening? What's nice, PyTorch offers you kind of nice standard building blocks for different things like linear layers. We'll get to convolutional layers and graph neural networks and whatever. For us, what's important is like a linear layer, and if you just create a linear layer object, it's the same type of Torch module, so somebody else wrote it for you, and it has parameters, weights, and biases, right? And so you don't need to think about it, and you can just start using these standard building blocks and build up your neural network. Okay, so then you can basically go from perceptron to a multi-layer perceptron, like by just adding a few lines. So we had for our perceptron only one linear layer and directly our activation, and then we run our forward through a linear layer and then through the activation. For a multi-layer perceptron, we then have like one hidden layer, so we have mapping to 100 internal nodes, doing our ReLU activation, mapping back to one output, doing our sigmoid activation, and then our forward is basically just passing the data through all of these different operations, right? And so this is exactly the type of multi-layer perceptron that you wrote in the exercise. One of the things in the exercise was to extend this to multiple hidden nodes. I don't know how many people managed to do it, but it was already painful. And here it's just a matter of, if you want 100 hidden nodes, you write this. If you want 1,000 hidden nodes, you write that. So it's trivial. Okay, so you can basically, instead of going through multiple lectures of deep learning, you can just do this by changing one line. Okay, so then, the entire point of deep learning is composition. And so, of course, I mean, there's nothing like the forward thing is all boilerplate. So it's exactly the same type of thing. The only thing is you're passing more functions through this thing, right? And so, like, there's no intellectual, like, gain in what is written in forward. And so this is also what PyTorch gives you. Instead of doing all of this boilerplate, you can just say, okay, I want to have a deep stack of a linear layer and nonlinearity, linear layer, nonlinearity, and so on. And you can just stack all the way and as deep as you want, and so on. And it's exactly the type of conceptual diagram that we had here on the left. Okay, so then finally we have our batch normalization. So all of these like neat little learning tricks that we have in machine learning end up as kind of pre-written. So somebody is all open source. So somebody thinks, okay, I read this nice paper, I add it to PyTorch. You might also contribute to open source software at some point. And so then, somebody wrote like a nice batch normalization thing. So it's like a complex type of thing that needs to keep track of like different types of activations and to take an average and blah, blah. But I mean, for you as a user, you just add one more line and boom, you have batch normalization. Okay, great. Okay, so then just on time, we have our full training loop. So this is like a state of the art. I mean, maybe not state of the art, but like a believable training loop. So we have our get data. So we have some data that gives us our input features and our labels. Now we want to train our model. So our model is our function object. So it has parameters. So it's our hypothesis space. And so we stick our parameters into our optimizer, right? And then we start learning. We start learning for like a fixed number of steps. We get some mini batch of data. So this is mini batch stochastic gradient descent, as we discussed. For the mini batch that we have, we stick it through our model. We get our network, like our predictions from our network. We compute our loss. So I didn't talk about this, but PyTorch gives you like nice pre-configured losses, of course. And then you have your empirical risk, right? And so now we want to do empirical risk minimization. Minimization means we need gradients. So we run automatic differentiation by triggering dot backward. So now all the gradients are there. Then we take our optimization steps. So that might use momentum, per parameter scaling, whatever. But in our code, it looks trivial. And so we just go, okay, improve. And then we reset our gradients. And then we track our training progress. And then, that is our training procedure. And so now the only thing that's left is we need to kind of define our model. And so we just do our multi-layer perceptron by using all of the nice little building blocks that we have, and we build boom train model, and then we're done. And so this is a nice little like end-to-end learning thing in one page. And so this is multiple lectures, so we worked hard to get there, but like practically to train a neural network, it's super easy. Okay, so then that's it for the week, and have a good weekend. Yep. Yeah.
The optimizer node.
Well, because the optimizer, so once I say dot backward, so then if I go back to the parameters and do like dot rad, there are values there. And so the optimizer knows where the parameters are. And so in the parameters, there are the gradients. And so that's how it knows the rate. So that's like the stateful nature of PyTorch. It's a bit. Okay.